Anyway, so thank you guys for being here, and let's get started. Yeah. So, and I hope this works. Oh, it didn't work. It's good that I can change it on spot. Give me 1 second, and I'll make that video work, because that's the only thing that I wanted to take from here is this picture. So let me just compile it again to make sure that it works. Sorry for the trouble. Yeah, so but anyway, I can already explain to you. So what you see here, and I'm compiling it to see that the video works, but what you see here is basically, not yet, it's basically the image here I'll show an animation for the periodic TASEP. So look first at this group of particles here. So you see just like this red line, but actually those are particles. You're gonna, once they start jumping, and now I'll be ready to show to you. Give me a moment, and I hope it works. Yeah, let me try again. Okay, back to track. Yeah, now it's gonna work. Yeah, so what you see here is the group of particles. So let's just fix over here. So this is a group of particles. They are grouped together, one after the other, and they're gonna run with the standard dynamics of TASEP. So the first particle is free to choose when its clock rings. The other particles have also independent clocks. So whenever their clocks ring, they decide whether they jump or not, and they're blocked for if there's a particle right in front of them. So this is like let's say one group of particles, and this group of particles has several copies here and here, for instance, right? So imagine that you just copy and paste this group of particles here, and then up front, and then up front, and so on and so forth, right? Such a way that you have a certain number of particles here, and you have a certain fundamental period here, right? There's a certain free space here, but right afterwards, let's say the first particle will eventually hit the last particle here in this group, right? Which then you should think about that as sort of all the particles now become correlated, right? At the beginning, the first particle doesn't feel the back one, but at some point when this first particle hits the very back one, the particles are all correlated. Okay, and as usual, what we do is that we look at the height function, right? Which you see over here, and you do that in a periodic way. So you put step initial condition here in the fundamental period, and then for all the remaining periods, you just copy and paste, but doing them in a continuous way. So this is what you see here, which is the graph of the height function. The dynamics is the usual one. Once a particle jumps, a down corner will become an up corner, right? So without further ado, let's make this run. And here's the dynamics of the particles. At the beginning, things are very slow, and they start speeding up. More particles are moving. And you see that right at this moment, one particle hits the other, which is to say that, let's say, the first particle hits the back particle, right? And now all the particles become correlated, and you'll see this sort of feature for the height function, which is somehow usual and, or like similar to one that you might have seen already for the TASEP. But let me just run it for one more time so that I want to show you one feature here. What you should see is that before the top particle hits, before the first particle hits the last particle, essentially, as I said, they are correlated, but right at the moment where the first particle hits the last particle, there is what we call a shock. So there, the height function sort of collides the position of the height function at the first particle hits the position of the height function at the last particle. So you have a creation of a shock. It's a distinct feature, and then right afterwards there are correlations between all the particles all together, right? So this is the dynamics of the periodic TASEP. And you can see from there actually that there are three distinguished regimes that were more or less already described in the literature, or they were described in the literature precisely. The first regime is what they call the super relaxation time scale, which is when the time is much, much larger than the period. So the periods, of course, eventually we're going to take both time and period very large, but imagine that the time is much, much larger than the period. So that means that there is already enough time so that the first particle has hit the last particle, and more particles have come all together, and all the particles are correlated, highly correlated. And in some sense, you can even imagine that in that regime, all the particles sort of are in such a rigid correlation that they all move together. So they more or less look like as one very big particle. And this is what's called the super relaxation time scale, corresponding to time much larger than period. And basically, if you start looking at correlations or fluctuations of the height function, that's going to be essentially the fluctuation of a random walk, so a single particle, and which means Gaussian, right? So, and another regime is when the time is much smaller than the period. So the period is becoming larger, and particles never exactly get so one group of particles never exactly gets to correlate with the next group of particles, which means that the dynamics is basically the standard dynamics for the TASEP. So you don't feel the period anymore, because the time, you don't allow enough time so that the particles correlate. Particles from different groups correlate. And this, in this super relaxation time scale, it's expected that everything should behave as just standard TASEP. And it's proven for some initial conditions, actually. And there is, of course, then an intermediate regime, right? when you're neither in one case nor the other, or it's expected to have a regime, which is what's called the relaxation time scale, which is, putting this way, exactly at the moment where all the particles become correlated, but let's say not strongly correlated. So if you look at the KPZ prediction, what we know is that spatial correlations happen at when the distance is proportional to t to the power 2/3, right? And that means that distance t to the power 2/3. So if you want the particles to become critically correlated, which means that you want to look at correlations exactly at the moment where the first particle hits the next group, this means that you should scale the period exactly in the same way as the spatial correlations. That is, the period should be scaled as t to 2/3. Right? So this is what's called the relaxation time scale. To my knowledge, this has been described in physics literature or predicted in the physics literature for quite some time, but rigorously mathematically, it only appeared in the past 4 years. So there was a work of Prolak in physics in 2016, and about a work of Baik and Liu. They appear in the archive more or less at the same time, but the Baik and Liu work is a mathematical work, so it took much longer to get published. And they describe the relaxation time limit for the 1-point distribution. So what you see here is the usual scaling that we do. So you look at the height function at location S and time t. You scale things appropriately. L, here's the period. I don't want to focus much on the constants. And so you look at the 1 point, the fluctuations for the height function, scaling according to relaxation time scale. And if you do things properly, what you get is that there is a 1 point limiting distribution, which they describe as follows. So this 1 point distribution depends on tau, which is the rescaled time, depends on gamma, which is the rescaled position. And this distribution evaluated at x is an integral over a small circle on the disk, a small circle going around the origin of a certain prefactor here, an exponential prefactor. And here you see the appearance of x and the appearance of tau, so the height variable and the scaled time variable. And then you multiply this prefactor here, this scalar prefactor, by a certain Fredholm determinant, where this Fredholm determinant here is of an operator k, which is a discrete operator that acts on a discrete space, on a small L2 space. It involves all the parameters, involves the parameter x, involves the parameter tau. It also involves the parameter gamma, and also involves the parameter psi that you integrate with. So let's say this is a spectral variable that you integrate to get the density. So all the parameters are involved. And well, to some extent, a little bit of a complicated operator. But they obtained the formula. The formulas of Baik and Liu and Prolog, they were somehow different, but recently Prolog showed their equivalence. Nevertheless, it's sort of a complicated formula, and at that point, they didn't study the distribution itself. They just, okay, there is a limiting distribution, right? And the question is, okay, what can we say about this distribution, right? Can we obtain certain qualitative properties or quantitative properties of distribution? Well, and that's basically our main goal in today's talk, is to describe certain nice features about this function, in particular, describing several similarities with the standard Tracy-Widom distribution. Right? And I must say here that this is also valid, and both works here, they consider the step initial condition. They also consider the flat initial condition. We also have results for the flat, but I'm not going to be talking much about that. But in the in the last few years, starting from that work, there have been many other works extending their results greatly in several directions. First, going from one-point distribution to multi-point distribution, right? Multi-location, multi-time, multi-height position as well distributions. Second, also extending to other initial conditions in the case of the periodic TASEP. Right? So, and this again, so this work that we are doing, we are also, this work that we're going to be talking about is about this one point in the step initial condition, but we are currently working on several extensions of our results for all the newly found distributions, case multi-point and also general initial condition. Okay, let's then go over that. But before going over the details, let's just remind ourselves about certain facts on the Tracy-Widom distribution, right? The GUE Tracy-Widom distribution, which, just remind you, describes the fluctuations of the height function, the one-point height function of the TASEP, take standard TASEP without periodicity, right? With the step initial, with the step initial condition. So there are several presentations of Tracy-Widom distribution. I am assuming that most of you are familiar with that, or at least with one of them. So perhaps the most famous one is the one that, or that's certainly the one that first arose, was the one given by a Faraday determinant. So the GUE Tracy-Widom, the Faraday determinant area operator acting on a real space, right? And the kernel of the area operator just takes some area functions and in this specific combination, right? So this is sort of classical. A second representation, which is perhaps not so well known, but has been around forever, is a representation in terms of an operator, which I'm calling here F, which is not exactly acting in a real space, but is acting on counters. Those counters will appear later on for us. How does that look like? So it takes certain counters here. I'm calling them lambda plus and lambda minus, should be sub-index. And then you just take lambda to be the union of those two counters, right? And then you will look at this operator acting on now two of those two counters, right? And yeah, and those counters, they just extend to infinity along certain angles, which are the angles, not by coincidence, the same angles that you can use if you want to use to write down some integral representation of the area function. And how does this operator look like? Well, it's a more or less similar form as here. So, and I write this down explicitly in the following way. So the kernel of this operator is a function, a vector function A of U, and this is a 2x1 vector transpose, and then you multiply by B, by a vector B of V, where again, this B is a 2x1 vector. I don't want to write them down explicitly, that's not necessary, but what's important here for us is that those vectors A and B, they take the following form. To obtain them, you take a certain vectors A naught and B naught. Those vectors A naught and B naught, they do not depend on any parameters. They do not depend on X. They're just characteristic functions. You multiply them by a matrix. So sigma 3 here is a Pauli matrix. And you just evaluate this Pauli matrix, just take the exponential of this Pauli matrix. When the exponential here comes with a cubic factor, right? And this is the important feature that I want to stress. And you see that exactly here is where the parameter X appears. So the parameter X, which is the variable distribution. So A naught and B naught do not depend on X, which is our parameter of interest, but X only appears in this cubic exponential factor. And of course, not by accident, this exponential factor is also the same that appears for the integral representation of the area function, apart from a factor of half. And the contours are also the same as I said. So you sort of do some transformation of this area determinant to obtain this representation for the area kernel. So you can imagine that the integral of the area function plays some role of inverse Fourier transform. And now you are transforming Fourier again, and you are obtaining something that doesn't involve the integrals anymore, but you have the exponents in a very simple way, right? Pretty formal, but that analogy is actually instructive and to some extent true. Okay, and a third, and perhaps the most, to some extent, it was the most surprised at the time it was found, but now most people are familiar with, which is the representation of the GUE in terms of the Hessian-Tacloid solution to Quastel-Remenik equation. So this just means that you should take the second derivative there should be a log here, right? If you take the second derivative of the log of the Tracy-Widom, you get that this second derivative solves the second Quastel-Remenik equation, which is a second order nonlinear equation. Important, it's nonlinear. Right? Okay, so these sort of several descriptions of the Tracy-Widom distribution, they might be useful for different purposes. But actually, if you look very carefully at the high function for the TASEP, the classical TASEP, it's described by the Tracy-Widom, which depends only on one parameter. But if you look at the position, right? We have the time, and we have also the height, right? So it's really like the 1, 2, 3 KPZ variable, right? And the explicit form that you can recover the one-point distribution for the high function of the TASEP is through these explicit change of variables. So you take this GUE, and then you look at it as a translation of the GUE, where this translation is exactly this form. It involves X here, which is the height variable, tau, which is the rescale time, gamma, which is the rescale position, and you combine them this way, and then evaluate the Tracy-Widom distribution, right? And then if you look at that, this is a function of 3 variables. So the high function for the standard TASEP is a function of 3 variables, or the fluctuations for the high function of the TASEP truly depend on 3 variables, although, of course, it's just such a simple transformation that no one ever cares about that. But anyway, we want to care about that. And just because it has some nice features and it's easier to compare the periodic TASEP if you do that. Let me just translate some of the facts of the Tracy-Widom in terms now of this new function that I'm calling FKPZ, so a function of 3 variables. So the first one, which is simple, is that if you look at the area operator and you play around with that, the representation of the area operator, and now you just address it with those new variables, what you obtain is that this fkpz can be written as a Fredholm determinant of a product of two operators, which actually those operators are the same except for minus sign. So this operator A here depends on gamma, depends on x, depends on tau. It acts on a real space, and it has a very particular structure, which is that if you look at its kernel, it's basically a shift out of one variable function where the shift x appears here. And this one variable function is almost like array, but not quite, in the sense that you introduce also a quadratic term here, and you also have the tau variable here, right? So it's almost like array, but it's actually a rescaled version of the array, right? And I want to highlight this cubic factor that's appearing here, where you have tau, the rescale time, you have gamma, the rescale position, and you have this u, which is the variable here for the kernel, which you should think of as x, right? So this, again, is just like a complicated way to write the array operator, but it can be interesting for comparison. The second one I'm going to highlight in a moment is the second representation that I showed in the previous slide. If you look at that representation in terms of the kernel acting on some curves on the plane, you basically get the same as before, but now before we had here just a cubic plus linear polynomial. Now we have a cubic plus quadratic plus linear polynomial. Now the parameters are appearing pretty much the same way. The vectors A0 and B0 are again independent of any parameters. They're the same that we had before, right? So two different representations. Of course, there's also a third, which is what happens with the Fellman-Vet-Lu equation. We'll come back to it later. Right? And I want to highlight that. Why? Let's now move to the periodic TASEP and see what happens over there. So here is I just copy and paste the first representation that I showed to you, which is when you dress up the one-point distribution of the classical TASEP with all the parameters x, tau, and gamma, when you get this sort of shifted array-like function. And for the periodic TASEP, our first result is a different representation of this one-point distribution. Remember that I showed before a few slides ago the result of Baik and Liu, which was saying that this one-point distribution was an integral of certain prefactor, the same prefactor here, times a Fredholm determinant. So what I'm saying here is that we obtain a different representation for the Fredholm determinant. And this representation of the Fredholm determinant actually should be here real space. Is of an operator that acts on L2 from 0 to infinity, pretty much the same way as this one. And it has a very similar structure as the one for what we're calling FKPZ. So this final determinant is again of a product of two operators, where you only change a minus sign for the gamma parameter. As I said, it acts on an L2 from 0 to infinity space. Little typo here again. The kernel is a shift of a given scalar function, exactly the same shift. And the only difference is that now you change this function, this function given by an integral, to a function given by a series. Where the series, so you sum over a certain set, I'm going to show to you in a moment. We have a certain prefactor here, which is independent of parameters, and you have exactly the same exponent here, right? Exactly the same exponent that you have for, let's say, the standard TASEP or for the array operator. And what is this S? The S is the set that appears here in the sum. This S is a discretization of this contour lambda minus. It's a specific one. Think of several discretizations, but there's a specific one, and this is what we call the beta root. So the specific form of the set appears in the derivation of the Baik-Liu formula, where they carry out the beta ansatz, and over there they have to find the beta roots, and then the set appears naturally in that analysis. But the definition is simple. The set itself does not depend on any of the parameters, but does depend on this variable z, which is the variable of integration over here. It's a spectral variable here. Okay? But what is interesting here as well is that this specific discretization is the one that encodes the periodicity. In the sense that if you look at this scalar function and you shift gamma by 1, this is the same because of the structure of the discretization. This is the same as looking at T of gamma itself multiplied by 1 over Z. And if you do that for the minus sign, then you get just Z instead of 1 over Z. And have in mind that you're looking at the kernel of the product. So if you look at the kernel of the product, the Z and the 1 over Z, they will just cancel out. So you get that if you shift this product, if you shift gamma by 1 in this product, you get that their kernels are invariant under the shift. And so the Fernald determinant is also invariant and whatnot. So this discretization is the one that's encoding this periodic structure in a very nice way. So that's one thing. And the second is that this factor here, omega, 1 over omega, that appears is roughly the spacing between consecutive points. So you can really imagine that this factor here is a discretization of this integral. But we also have this Q, which is a polylog function. At this stage, we don't have a specific, we don't have an interpretation for this Q. It is what it is, but it's independent of any parameters. It appears in the analysis, this polylog function. But I guess the important part is it's really independent of X, gamma, and tau, which are the physical parameters, right? Anyway, so main message here, pretty much the same structure that you have for the 1 point of the TASEP, we also have for the periodic. The only distinction is that whenever you had some integral or some continuous type of object, you now have a discrete type of object for the periodic. So so you can see that there's a certain analogy between Fourier transform and Fourier series. To some extent, this looks more or less like Fourier series, which encodes periodicity. And then the beta roots encode this periodicity very nicely. And here you can think of it as sort of Fourier transform itself, right? So it's a nice analogy between them. Okay, the second different representation that is also interesting for us that we obtained is in direct comparison with the other representation of the Tracy-Widom that I showed to you before. Recall that that representation of the shifted GUE was in terms of the Fredholm determinant acting on certain contours on the plane. Those are the blue ones, the lambda ones here. And just to remind you, the kernel was sort of a inner product between two vectors divided by u minus v. And those two vectors had this specific structure that they were multiplied by certain cubic prefactors, right? And here I'm already putting here those dots and those squares. So those dots and squares are exactly the beta roots. Before I only needed beta roots on the left half plane, but now I'm gonna need also beta roots on the right half plane. And the contour gamma here in blue is exactly the contour where this shifted GUE So the second result is again just a different representation of the distribution. The integral, the sort of spectral integral, is still over there. So integrate certain prefactor times the Fredholm determinant, but we change the Fredholm determinant to a new one, where this new operator now acts on a discrete L2 space. This S is like the set of beta roots, so the dots and squares I showed to you. And the structure of the kernel is pretty much the same as before, with new functions here, but the dependence on the parameters is exactly the same. So you have that the kernel is an linear product of two vector functions divided by u minus v. Those vector functions, they're given by some fixed vector functions. Those vector functions will contain the Q, will contain characteristic functions, don't bother, but they're independent of X, tau, and gamma. But more importantly, those fixed F naught and G naught, they're multiplied by certain prefactors. And those cubic prefactors are exactly the same as the ones that appear over here. And you see, and I hope this is already in your mind, but let me stress that for the standard FGUE or shifted FGUE, we introduced back the parameters tau, gamma, you can think of that in an artificial way, because why should you look at that if you have already Tracy-Widom as a function of one variable, right? Just work it as a function of one variable. But for the TASEP, everything truly depends on the three parameters. You have there are no three, this delimiting distribution, this distribution F is really non-trivially depending on all the parameters. So you don't have that, you just cannot reduce everything to, let's say, a function of one variable. So you really need to have those three parameters. And once we now introduce back the shifted parameters in the GUE, we believe that comparison is more fair, so to say, right? So there's more of a direct analogy between them, right? And again, it's striking, perhaps not so much, but first time we saw it was sort of somehow striking that we obtain exactly the same cubic polynomial here, right? And there's more to that. There's more that we can do because of that. Okay, so far so good. And I hope I still have time. Okay, so let me just.
I have one question, sorry. So just to make sure, so the tau is the scale time, x is the scale position, and the gamma is the scale height function? I don't know.
No, scale position is gamma. The scale height function is x. Or if you prefer the distribution variable, right? You look at height functions more equal than x, right? So x is the scale version. Right? So the gamma position for me is the position on the TASEP itself.
So usually you would look at basically x is the meaningful variable, and then you would look at the time, and you would cancel out gamma.
Yeah, exactly. You just shift time and gamma together to cancel that out in the GUE, right? Okay. or in the classical TASEP, right? But here you cannot. You simply cannot, right? For the periodic. Okay, there's this new representation. So we have lots of different presentations, and the point is, what we do with that, right? But I want to highlight this feature. So here I'm just copying and pasting here. So H is the one for the periodic that acts on a discrete space, and F is the one for the non-periodic TASEP, which acts on a continuous space. And the structure is the same, right? They're sort of inner products of functions. Why do we care about that? Let's see. So if you look at that carefully, what is the structure? The structure is that, as I highlighted several times, that this kernel is just the inner product of two vector functions divided by u minus v, right? So you can think about that as like sort of finite sum, where phi k's and psi k's are just the entries. And these operators which have kernel of this form, they are called IIKS, or it's Zergen-Korepkin-Slavnov integrable. And so here's like a word that we all like, in integrability, but now we're talking about integrability of kernels, not necessarily of probability, although now they come together, right? And we say that they're integrable if any kernel that has this form is said to be integrable. Okay, why we care about that? Well, it's a nice structure. Once you find a nice structure, you might try to find nice results that hold for this structure. And while you do find lots of examples of such kernels, Airy, for instance, Bessel, Sine, lots of other examples appear in this way. All sorts of different critical kernels in the matrix theory, at least some of them do have this structure as well. So there are lots of nice things that you can see, that lots of nice examples that kind of motivate you to study them. And important, perhaps one of the important things here is that there's a canonical way to associate to an integrable operator, Riemann-Hilbert problem, or a nonlinear Fourier transform, which sort of provides you with several tools to do all sorts of things. We're going to talk more about that, right? But in particular, Riemann-Hilbert problems are very suitable for asymptotic analysis. Again, I'm going to perhaps mention a few words later on. But anyway, the point is that once you identify the structure and you look at its Riemann-Hilbert problem, you have several tools to do several kinds of things that you may want to do. And we try to explore that a bit. Right? Yeah, so let me just explain to you how this connection to Riemann-Hilbert problems here work. Again, general setup, you start with a kernel acting on, it can be either a small L2 space or let's say a standard capital L2 space over a set A. So A here could be either discrete or let's say a curve on the plane, right? The human-Hilbert problem is as follows. So you look at a matrix value function of size L. L here is the number of, it's the size of those vectors. So for us, L is equal to 2 in the cases that we're studying. But anyway, in the general case, just look for a L by L matrix value function X, which is analytic. So the entries are analytic everywhere on the plane, except at the set A, where your kernel is acting on functions defined on that A, right? And then there are two distinctions. If you look at discrete, if this A here is a discrete set, then of course this matrix X has isolated singularities at the point A, and you ask for those singularities to be simple poles and to have a specific residue structure. When you compute the residue, this is the same as multiplying the matrix X by a new matrix, the residue matrix R. And this residue matrix is the one that ties together with the kernel. So what you do, the kernel looks like phi transpose psi in variables U and V, and the kernel does more or less, you just change the transpose, so you look at phi psi transpose. So this inner product is a scalar, this gives you a L by L matrix, right? And you also look at that as the same variable, let's say S. Here they've evaluated different variables, but here they evaluated the same variable S. Right? Okay, you compute this residue and impose that you try to find a function X with simple poles there with this specific structure. Again, don't care too much about the structure, but essentially it's saying that the residues of, let's say, certain columns of X, they are related with the behavior of other columns of X in a certain way. Okay? Described by this matrix R. Right? And this is for A discrete, but as I said before, there's also the case when A is a counter, as the one that we considered before with lambdas. In that case, so you don't have exactly like isolated singularities, but what you ask is that your matrix value function X has continuous boundary values when you approach the plus side or the minus side of the contour, and they should be related in a specific way. X plus should be equal to X minus times J, which is what they call the jump matrix J. And this jump matrix is computed in a very similar way as the residue matrix, except that now you have this identity minus phi psi transpose. Right? They're almost the same. Right? And again, the jump matrix is the one that connects back to the operator that they started with, right? So what I'm saying is you look at a analytic function, which analytic of the set where your operator is acting, has either residue conditions or poles in this underlying set, has either residue conditions or jump conditions in this underlying set A, and finally you also normalize this function X to look like identity at infinity, perhaps with a residue which is going to be relevant for us, plus some smaller order term, right? When S goes to infinity. Right? Okay, so there's a problem, find X with those properties, and the theory tells you that there exists a unique solution if and only if the Fredholm determinant of the operator is non-zero. In that case, you can compute. In that case, you can compute also the resolvent of this operator induced by K. And more important for us, in several concrete cases, you have Fredholm determinant. And in our specific case, it reads as follows. So if you take if you suppose that X depends on a parameter, in our case, it's going to be X, you take the derivative of, with respect to that parameter of the log of the Fredholm determinant, and that is just like the 1-1 entry of the residue of X at infinity. So if you know X, you know the log derivative of the Fredholm determinant. Super simple. These identities specific to, let's say, the cubic weights, it could be generalized in a certain way. But typically what you have is that you have a very simple expression, perhaps involving other entries of X1, perhaps X2, X3, X4, few of them, right? But message is, once you know the solution to the human-Hilbert problem, it's simple to recover derivatives of the log of the Fredholm determinant, right? So this human-Hilbert problem encodes not only the operator, it's Fredholm determinant, it's a resolvent, but also the Fredholm determinant diagonally. Right? Okay, so let's just describe everything that we have in our specific setup, right? As I said, remember that this cubic factor appeared several times for us. And for the periodic TASEP, we are acting on the set of beta roots, so a discrete set A. In that case, if you compute the residue matrix, it's very simple. It's going to look as R0 matrix here in the center, and I'm conjugating by some matrices, by a matrix which is computed out of V. Right? This R0 again is independent of all the parameters x, gamma, and tau. Just contains like some characteristic functions and some polylog, but it's simple and independent of parameters. And for the TASEP, so for let's say the Durst version of the GUE, if you do all this mumbo jumbo, the jump matrix, now we're acting on a contour, so we have a jump matrix on the residue matrix, but it has exactly the same structure. It's just a matrix independent of parameters, conjugated by a matrix which is computed out of this cubic polynomial V. Right? So the structure is exactly the same. Right? The question is, okay, so what do we do with this? Right? Okay, we had the Riemann-Hilbert problem, we have this jump, it's relatively simple, and what do we do with that? So just to give us some sort of idea about this Riemann-Hilbert philosophy, and one of the reasons why it's kind of relevant is the following. Imagine that you know, let's say, your original Fredholm determinant for some set of parameters. For simplicity, I'm putting here x equals 0, gamma equals 0, t equals 0, just because when those are all 0, I'm basically considering just R0 or J0, right? Those exponential factors are just identity. So it's something very simple. Imagine you know your Fredholm determinant for some very simple parameter, and you want to find actually for all sets of parameters. So you look at that, so to speak, as an evolution in all the parameters, right? Again, think about Tracy-Widom. Imagine that you know the Tracy-Widom, you know the area determinant, the area kernel determinant for one value of x, and you want to evolve it. You want to find for other values. What you do, you put in the area this value in the Painlevé equation. You evolve the Painlevé equation, and you get the Tracy-Widom distribution evolved. Right? So you can imagine that this evolution could be governed by an ODE or a PDE or something else, right? But there's certain evolution in the pipe. And one of the beauties of the Riemann-Hilbert, this Riemann-Hilbert problem is that once you set up, let's say, the parameters to 0, the data that you need to compute is very simple. These are not or J not, which, as I said, basically just involves characteristic functions that does not involve parameters. And then you evolve the parameters in a very simple way, which is basically linear. What you do, you just tune up the coefficients of your polynomial. So it's basically a linear evolution, or exponential linear if you prefer, but super simple evolution. Right? And if you know how to compute that, basically now you just solve your Riemann-Hilbert problem for the evolved parameters, and you get back the Fredholm determinant that you want for the evolved parameters. Right? So far, so good.
So can you explain again, how do you go from R0, J0 to RJ?
Just look at here. You have R0, you just conjugate by matrices, and then you matrices that are computed basically depend basically linearly on the parameters, right? Here from this perspective, right? So very, very simple, right? Of course, the problem is, okay, can you solve the Riemann-Hilbert problem? That's another deal. But at least the evolution, so to speak, is very simple. Right? Perhaps let me see if I get the time. And yeah, perhaps I can spend 5 minutes doing some little math here for you to see how one could use that to do one specific. Okay, so let me see. Let me just find the right window here. Here. Let me see if this is gonna work. Just one moment. I just want to show you the calculation that you can get from this, right? Just 1 second. Yeah. So can you see me writing? Yes.
Yes.
So just to, for instance, do a very simple calculation on how to get point of equation of these or other equations, all of that. So just to illustrate, let me just write this matrix J of S, which is the jump matrix, which is E of minus V over 2 sigma 3, J naught, E of V over 2 sigma 3. Don't bother much about how those look like. They're just matrices, right? And remember that the jump condition tells us that J plus of S equals X plus of X equals X minus of S times J of S, right? So now, what do we define? We define now a new matrix, which is Y of Z, which is gonna be just X of, or Y of S, I should say, Y of S equals X of S times E of minus V over 2 S sigma 3, right? So this, I'm just defining a new matrix. I'm just transforming my X to a new matrix. Why? Well, this factor here is analytic everywhere, and this factor X is analytic except possibly the counter. So from that, you already see that Y is analytic is everywhere except possibly the counter. Then you can compute the jump of Y. What's the jump of Y? So again, Y plus, if you compute that, that's essentially X plus times the Z of minus V over 2 sigma 3. And then just put here X plus. What's X plus? This is exactly, it's just X minus times J of S times the Z of minus V over 2 sigma 3, right? Look at that. This E of minus V over 2 is going to cancel with this one, right? So what I get is just X minus E of minus V over 2 sigma 3 times my J naught. Yep. Very simple calculation. Well, but this other factor here is exactly Y minus times J naught. Yep. Far so good. Very simple calculation. Oh, but this here is independent of parameters. It doesn't depend on X, Y, X, gamma, and tau, right? Which means now that if I take a derivative of my Y, I get exactly the same jump condition. Again, derivative with respect to parameter, right? I get exactly the same, exactly the same jump condition. And then if you do exactly the same calculation that we did before, what you're gonna get is that this matrix here, the derivative with respect of parameter times Y minus 1 is entire. Because the jump for Y and for partial Y are the same, you just repeat this calculation, but now for this new matrix, and you're gonna see the jumps cancel. And the jumps cancel means that this function itself here is entire, right? But then you look at infinity, right? And you know that this Y times partial Y, you're gonna have some X factor, which looks like identity. The drop down, which is polynomial, and the exponential parts remain the same for partial Y, and the exponential parts of partial Y will cancel the exponential parts of Y inverse. And only the polynomial part, which comes from the derivative of this factor here, is going to remain. In other words, by Liu view, if you do this calculation, what you're going to get, and again, it's basically algebra or calculus, you're going to get that partial Y is equal a certain matrix A times Y, where here A is a polynomial of degree at most 3, depending on the degree of your polynomial V here, or depending on the derivative here, right? So V here is for us a polynomial degree 3. If you take the derivative with respect to T, you still get that A is a polynomial degree 3. If you take the derivative with respect to gamma, is a polynomial degree 2. With respect to X, a polynomial degree 1. Very simple. Oh, but this here, this little thing, is just a differential equation. It's a linear differential equation. Oh, you have 3 different linear differential equations. One for x, one for t, one for gamma. You combine them, and then you start doing all the mumbo jumbo, and what you get at the end is the result I'm going to show to you now, which only has to do with the fact that you have. Oh, let me just put here full screen mode. So all this that I showed to you is soft in the sense that the thing that you need is only that first you're dealing with an IIKS operator, integral operator, and second that either the residue or the jumps, they have this V factor over there, nothing else. And what you get when you do this mumbo jumbo is that, and there should be a log here and there should be a log here, sorry for that. But you get that the log derivatives for the Fredholm determinants, either for the periodic TASEP, which is here, or for the dressed up GUE, they satisfy a couple systems of mKdV equation or a couple heat equation. Both of them satisfy a system like this, right? So more precisely, the second log derivative splits as a product where each term here satisfies those equations. There are certain symmetries between P and Q. You can reduce that to one single equation, but a non-local equation. I don't spend much time on that. And the point is that once you combine those two, you recover a result that appeared recently in the literature, which is a KP equation. So the second log derivative of this Fredholm determinants, they both satisfy the KP equation. Right? Going back to things that I mentioned to you earlier, remember that the FGUE satisfies the Tracy-Widom distribution. And you remember that then we dressed up all the variables back to the GUE so that we study the 1 point distribution for the TASEP. And basically what this is saying, if you enforce now U to be essentially a change of variables of a function of one variable, you recover Panavet2 equation. So this is basically really just like the sort of what will be, or the right way to say is that the Hasse-Macleod solution to Panavet2 equation is nothing but a self-similar solution to the KP equation. So in that sense, it's a result that was already new, that was already known, right? Anyway, we covered the KP equation, which is an equation in 3 variables, right? Sort of a generalization of KdV. And again, let me stress that everything that basically one needs is this factor V here and the integral structure on the line. But several comments are due. For TASEP, the Quastel TASEP, not the periodic, this KP equation was recently refound. Right? We knew before P2, but the connection to KP was recently refound by Quastel and Remenik, perhaps 1 year ago. And it was funny because at that point, we had the system, and we didn't know about KP. And they say, hey, but there should be KP, right? But once you know what you're seeking for, you'll find KP. Right? We had a system where we didn't have a KP. Once they posted, like the next day, we had a proof for KP. Right? But for us, so for periodic TASEP, this is new. For TASEP, was not new, just a recovering result of them. And their result is actually more general in the sense that they consider multi-point one time. So one time variable, but several locations. And they have still a KP equation, matrix KP equation. We also recall we're also able to get a KP directly without going through those coupled systems, without going through integral operators, using a different approach that we also learned from Quastel-Remenik. And this is valid for general AC. So for general initial condition for periodic TASEP, we don't know if those coupled systems are there, but we do know that the KP equation is there, right? And just to get some little idea on how it comes, again, it has to do with this cubic polynomial that appeared all the time for us. And we do some work. So the distribution for the periodic TASEP of general initial condition, I guess, was posted perhaps in December or very recently by Jipeng and Liu and Jinho Baik. They have a certain operator acting on better roots. We transform them here and there. And what we get is that the kernel, there is a certain operator appearing. You integrate the Fredholm determinant of the operator. Okay, very similar. But anyway, at the core of it, there is this Fredholm determinant of a certain operator, which after we dress it up, it becomes of this form, where again, the cubic polynomials are appearing over here. And there's just very few things that one needs to go to know to get KP. And those are basically some identities between parameter derivatives of the kernel and variable derivatives of the kernel. Once you have those identities, which are basically coming from this cubic polynomial, you're done. You get KP equation. But as I said, for the periodic TASEP, we also, for general initial condition, we don't have this full structure of integrable operators, but for periodic TASEP with step initial conditions, we do. And from that, we also learned that for periodic TASEP, we have soliton solutions. But for the classical TASEP, well, it's Tracy-Widom, so it's not solitonic. It's non-localized in space. You have oscillations in one end. And as I said, there's also for flat initial condition, we can also say more, and we connect it to KdV equations. Not KP, but sort of there's a reduction there of KP that becomes KdV in that setup. Very briefly, moving towards the end, actually, all those things that we discussed, they are very nice. They give very nice structural representations of the periodic TASEP, but the point is, okay, what do you do with that? And it's funny because we obtained several different representations for this threshold determinant that appears in the periodic TASEP. Different representations are useful for different purposes. Okay, one representation in terms of integrable operators, we obtain those PD systems. The other representations, we use some of them to obtain, for instance, the convergence to Gaussian for a long time. Again, so imagine that long time means the super relaxation time scale, and now the particles are highly correlated, so they look more or less as one single particle. And we can study that asymptotic regime, and we get indeed that this distribution that generates the Gaussian. So the distribution of the periodic TASEP that generates the Gaussian, as it should, from intuition at least. We also have small time asymptotics, super relaxation, which means that we should the period is much smaller than time, so we should expect that TASEP, the filtrations for classical TASEP should appear, and that's what we get. But for technical reasons, we only get that when gamma equals 0, so centered, position 0. The proof for general gamma turns out to be a lot more complicated. Anyway, we have this designation, at least for one specific parameter. We also study tail behavior, large tail behavior. Don't care much about all the quantities here, but basically what they're saying is that the periodic distribution for the periodic TASEP is comparable, the large tail of it is comparable with the distribution of Tracy-Widom, shifted Tracy-Widom. This H is my shifted Tracy-Widom, except for exponentially small corrections. So they agree up to exponentially small corrections. So sort of in the large tail behavior, you don't feel much the periodicity. Right. Okay, okie. So perfect, moving towards the end, let's just wrap up what we discussed. So we found, first off, we found several different presentations for the kernels, and that could possibly be of interest for different reasons. And we discussed how they are connected to integrable systems. And I hope I could highlight enough that basically we need very little. And one of the key ingredients, perhaps the most key ingredient, was that all those threshold determinants involved certain cubic there. And this cubic, the potential is the one that gives rise to the whole integrable structure, the KP equation, or the couple systems, right? That was very sort of one of the key aspects that had to be there to get the KP equation at the end. As I said, we are currently studying also multi-point distributions for both TASEP and pTASEP. Multi-point, I mean multi-time as well, multi-time, multi-location, multi-height. We already have all sorts of generalizations of the connections with integrable systems. We have multi-point versions of KP, of also nonlinear heat, nonlinear heat system, nonlinear mKdV system. We also have for the TASEP, not the periodic, but for TASEP, we also have a matrix version of Painlevé-2 equation, or several matrix versions of Painlevé-2 equation. Those are, but We're still working also on the possible asymptotic results from there, so it might take a little bit still to get that announced like on the archive, but still we're working on that. Human-Hilbert problems arise in this, as we saw in this context, and they give us a good ground to find all sorts of possible connections. You obtain some asymptotic results, the ones that I mentioned in the previous slide. The generations for super relaxation times k or stale behavior with different methods using different representations. We haven't explored much the Human-Hilbert problem in terms of asymptotics. For instance, the large and negative tail of distributions is known to be much more challenging typically, but Human-Hilbert problem is very suitable for that. We haven't explored that yet, but certainly one of the things on top of our to-do list. And we believe that's now within reach using Human-Hilbert methods, for instance. And I should stop over here. Thanks a lot.